This video lecture covers the integrated rate law. With all of the work that we've done on rate law so far, the only thing we haven't done is create some graphs or plots that also tell us the same information that the equation is showing. So I want to make a couple of these, and then we will turn them into, or just I will give you, I'm not going to derive it for you, the equations that actually govern what we're trying to show in our pretty much qualitative plots up until now. So just kind of going in order with the really common rate law orders that we have looked at. If we had something like a zero order reaction, so you know this very well at this point, but the rate is just equal to the rate constant because that exponent was zero. There are a couple of graphs that usually show up in cases like this. So one would be something like rate versus reactant concentration. And so this, you could pretty much pick up. We take a minute to think about what we're actually asking. So the rate in molarity per second versus the concentration of A. If it's zero order and there's absolutely no dependence on the concentration for the rate of the reaction, just whatever my rate is, it's just constant, regardless of the concentration of the reactant. All right. Now, the other plot that is very useful that we like to look at is reactant concentration versus time. So, get this set up. So, concentration of A versus time. So, kind of qualitatively thinking through this, if my rate is constant, then as my reaction goes, my concentration of A starts out at some value, and then my reaction is just kind of chugging along, and as it chugs along, the concentration of A just decreases at a steady linear rate until you run out and the reaction stops. All right, so that's zero order. For a first order reaction, so now remember, rate equals K times the concentration of A to the first power. If we did rate versus concentration of A, and our rate has the same molarity per second units, concentration of A, this plot, right? So just like the rate versus concentration of A that we looked at for zero order, this is just dependent on the rate law. So it's sort of a graphical depiction of what we saw in the data tables. So if the rate is directly proportional to the concentration of A, as my concentration of A increases, my rate of reaction will increase, and it'll do so in a linear fashion. So rate versus concentration of A, as you increase A, the reaction goes faster. So when I do my reactant concentration versus time plot, starts to look just a little bit different. So time, concentration of A. So I still start out with some concentration of A, right? I have to. And then my reaction, if my concentration of A is high, is going pretty quickly, right? So I might see that my concentration of A starts to drop pretty fast. But as my concentration of A goes down, my reaction slows down, right? So lower A, lower reaction rate. So it's still going away, but maybe not as fast. But now my concentration of A is even lower, so it starts to go slower. And then it gets lower and slower. And eventually it'll run out. Now that we'll have space on my plot. But it's no longer linear dependence because as my reactant concentration goes away, my reaction is slowing down the whole time. All right, so let's take a look at second order. So now we're at rate equals Ka squared. So we're going to do the same plots. So rate versus concentration of A. Rate again in molarity per second. So this time, it's still a dependence, right? As my concentration of A increases, the rate of my reaction increases, but now it's to the second power. So where my first order reaction looked like a y equals x plot, this is going to look like a y equals x squared plot, right? So I start out at 0. As my concentration of A goes up, the rate starts to increase much more quickly as the concentration of A gets higher because of this concentration of A squared dependence. Which means when I look at a plot of concentration of A versus time, I will see a similar effect to what I saw in the first order plot, right? I start out with some high concentration of A, which means my reaction is going very quickly, right? My concentration will drop really fast because the reaction is going quickly. But as it drops, this reaction slows down a lot because of the x squared dependence. So we'll see this taper off and the reaction will go much more slowly as my concentration of A decreases. So what we have done is just kind of qualitatively reason through what all of these reactant concentration versus time plots might look like. What the integrated rate law does is give equations for every plot in this column. So in some bullet point kind of words, what the integrated rate law is doing the first thing is that it is showing the relationship between concentration and time. It's going to be an equation that matches those lines that we've had. It does this by bringing together the rate law and the definition of the rate. So far we have done two things where we've written rate equals, right? So we did this for definition. We did this for rate law. Well, guess what? These two values also equal each other. So if you set the definition of rate equal to the rate law, and then do just a little bit of calculus that we are not going to do, you get the integrated rate law. So it really is integrated, as in integrated over time. So what this means, because the rate law is an important part of it, it means you must know the rate law in order to use the correct equation. So each rate law will have a specific integrated rate law to use with it. Now, the good news is the equations are labeled on your equation sheet. So I'm going to give you here what these equations look like. Right? The integrated rate law for zero order looks like the concentration of A at time t equals negative KT plus the concentration of A at time 0. So the T is time, the K is still the rate constant. So all of these values that you would have put together in finding the rate law or would be given to you in the problem, but this equation only works for zero order. So from maybe a table of data or the information given in the problem, you would know that your reaction is second order. And then when you go to the equation sheet to look for the appropriate integrated rate law, this is the equation you'll see, and it will be labeled as zero order. For first order, I'm going to give you two forms because some places report very different ones, and it's just a little bit of algebra that differentiates the two. So in this sort of long written out form, the first order integrated rate law is the natural log of A at time t equals negative KT plus the natural log of A at time 0. Or if you move this natural log of A at time 0 over to the left, you have a natural log minus a natural log. So you can write it as this stacked fraction instead, which sometimes you'll need to do depending on what you need to solve. You could write this as the natural log of A at time t over A at time 0 equals negative KT. So this is really useful if you have something like a problem that says 75% of the reactant is remaining, and it's asking you to find out how long that is, or asking you to find the rate constant for the reaction based on that. You would know that the ratio of A at time t over A at time 0 is whatever that percentage was. I think I said 75%. So 0.75 in this, for example. Right? So this is the only form of the equation that would let you continue to solve unless you put the numbers in separately in the first order equation that's above it. Right, but you can see that there might be scenarios where you need this rearranged form. So again, this will be labeled as first order on your equation sheet. For second order, start to look a little weird. It's 1 over concentration of A at time t equals a positive KT plus 1 over concentration of A at time 0. And I'll just underline this as well. This will be labeled second order on your equation sheets. What's also useful about this is that all of that data that we have seen to use to determine the rate law, you could use that to have another way to find the rate constant. So far, what we have talked about is that you could, for each trial, plug all of the information into the rate law and calculate K that way. Now, in order to do it properly, you would have to do this for every single trial and then take an average and some kind of standard deviation to calculate error. But you could also create these straight line plots where you can get K graphically. So once you know the order of the reaction, you could create this plot. Or if you want to make sure the order of the reaction that you've calculated is correct, you could take your data and start to put it in these different forms of plots until you get a straight line. Because each straight line plot will come from a different way of plotting the data. And I am not going to ask you to create these plots, but I could potentially give you this information and ask you to determine what the rate constant is from the already plotted data. Now, you would have all of the information. I'm not going to make you do any crazy guesses. So you might, get the line equation where you just have to pick out the slope or something. So for zero order, what this looks like, if you do a plot of the concentration of A versus time. Hopefully you expected this because we did already see it as a straight line plot. The slope here is equal to negative K. So once you know the slope of this line, all you have to do is take the opposite of it, and that will give you the rate constant. For first order, if we plot the natural log of the concentration of A versus time, this will be a straight line. And again, the slope here is negative K. For second order, it gets a little bit weird looking. Just in terms of what we're going to plot. We're going to plot 1 over the concentration of A versus time. So if you think about what this is going to look like, at the beginning of the reaction, the concentration of A is high, so 1 over A is low. So your plot starts out low, and then as the concentration of A goes down, 1 over A goes up. So your straight line plot has a positive slope, which means here the slope is just directly equal to K. So the other thing that this would tell you is that if you made a plot of the concentration of A versus T and it was not a straight line, then you don't have a zero order reaction. So you can get some extra information that way. All right, I want to do one example problem that shows using the integrated rate law. And then I want to talk about an application of the integrated rate law that you're probably already familiar with, without maybe necessarily knowing it. So the problem that we're going to do, I'm going to actually pause recording, write the problem, and then read it to you. All right, so this question says the decomposition of SO2Cl2 is first order with a rate constant of 2.90 times 10 to the minus fourth 1 over seconds. What is the concentration of SO2Cl2 at 865 seconds? The initial concentration is 0.0225 molar. Now, we don't necessarily need a balanced equation for this, but I do find that it is nice to have. So we're talking about the decomposition of SO2Cl2. It is a gas. It turns into SO2 and Cl2. All right, so what we're looking for is a concentration at a later time. So we need the integrated rate law to do this. And the information that we need in the problem to do this, first of all, is that it's a first order reaction. So because it's a first order reaction, we need the first order integrated rate law in order to solve this. So we're going to need natural log of A at time t equals negative kt plus the natural log of A at time 0. We will also need the rate constant, which is given, and then what time frame we're looking at. So something that I think is really helpful to start out, and you don't have to do this, but you might find it helpful, is I'm just going to rewrite this with the stuff in it that I'm actually going to solve for, right? So we're talking about the natural log of the concentration of A. The natural log of the concentration of SO2Cl2, and time t is 865 seconds, right? So that's just a subscript to label it, meaning this is my later time concentration. And it equals negative kt plus the natural log of the concentration of SO2Cl2 at time 0, right? Which is just also our other way of saying initial concentrations. So now I know where I can plug things in and exactly which piece I'm solving for, right? I want the concentration at 865 seconds. So, I mean, very nicely, this is already solved for that. So everything I plug in will be on the right-hand side, and I just have to plug the numbers into my calculator to get the answer that I'm looking for. So let's plug those in, right? We're looking for SO2Cl2 concentration. Well, we're going to solve for the natural log, so I guess we have a little more to do after that. Equals negative K is 2.90 times 10 to the minus fourth 1 over seconds. T is 865 seconds plus the natural log of 0.0225. So also the thing to watch out for here is that you're using your natural log button now and not your regular log button. So natural log of SO2 Cl2 at 865 seconds equals, this is negative 0.251 from this first part where you do the rate constant times the time. And then the natural log of that really small number is negative 3.79. So the natural log of SO2Cl2 equals negative 4.04. And now exactly like we did 10 to the whatever power to get something out of a log, to get some base 10, to get something out of a natural log, we'll put both as the exponent for e because it's a natural log. So that will get rid of this log. And so we'll be left with the concentration of SO2Cl2 being equal to e to the negative 4.04, which is 0.0175 molar. All right. So at this point, you can do some quick checks on your answer, right? We want to make sure that this concentration is lower than the initial concentration, which it is. And we want to make sure that it doesn't go negative, because if you ended up with a negative answer here, it would just mean that you had fully run out of reactant sometime before the time point you're trying to calculate. And your reaction isn't going to keep going if you've completely run out. So your time point is wrong, or, I don't know, Dr. Lutz made a mistake in writing the problem, or something along those lines. Okay, so the really big thing that goes with the integrated rate law is this idea of half-life, which we label T1/2, and this is just the time required for the concentration to reduce to half its initial value. So this comes up a lot with things like radioactive decay. Because if we have something that is radioactive, we want to know how long it's going to be around, especially if it's doing something like causing damage or to people. This can be the cause of a lot of cancers if you have radioactive waste accumulated in a space. And so the half-life will tell us how long is this really going to be around here. So there is a derivation that I will not make you sit through, but this is just a rearranged version of the integrated rate law. So just definition that might be helpful. We mean that the concentration of A at time t equals 1/2 the concentration of A at time 0. So whatever you started with at the half-life, we've used up exactly half of it. So what this means is that for a zero order reaction, I'll give you these in order. For a zero order reaction, the half-life, so T1/2, so this can be some time in seconds, is the initial concentration of A divided by 2 times the rate constant. So T1/2 has a dependence on A. And as your concentration of A goes down, your half-life gets shorter. We'll see what this looks like graphically with one of our examples in a little bit. As A decreases. So you have some concentration of A. It takes a specific amount of time to get to half its amount. At a lower amount, it takes even less time to cut that value in half. For first order, we now, interestingly, don't have a dependence on A. So a T1/2 for first order is 0.693 divided by the rate constant. So there's no dependence on A, which means we have constant length half-lives. So regardless of the amount that you have hanging around or in your body, for example, with medications, doesn't matter how much you have, it takes the exact same amount of time to cut that value in half if it goes by first order kinetics. Second order, this T1 half equals 1 over K times the concentration of A initially. So second order, it again is back to having a half-life that depends on the concentration of A. But as your concentration of A goes down, this is in the denominator, your half-life goes up. So T1 half gets longer as A decreases. So if this is a radioactive waste that decays by second order kinetics for some reason, this is really bad, right? As your amount goes down, it takes you even longer. So it takes a lot longer for all of it to go away if it's going by second order kinetics. So I want to do a little bit of a plot. I want to do the plot for first order. And we're just going to make up an example here. So first order, and I'm going to say that the half-life is 100 seconds and the initial concentration of A is 1 molar. So hopefully I've given myself some nicely spaced plots here. Well, we're just going to guess. We're going to say that this is 1.0 on our molarity scale, and that my time down here in seconds, right, and this is 0. So if the initial concentration is 1 molar, so we're going to start out up here at 1 molar, and my half-life is 100 seconds, and I'm first order. So there's no dependence on the concentration of A in our half-life. So if I pick some time interval, say that this is 100 seconds, it will take me exactly 100 seconds to go from 1 molar to 0.5 molar, which is half of the initial concentration. So, assuming I've marked this right, 0.5 molar should be there. So at 100 seconds, I'm at 0.5 molar. So another 100 seconds later, I am at half of 0.5, so I'm at 0.25 molar. So exactly 200 seconds, 0.25 molar. And I could go out another 100 seconds, and I would be at exactly half of 0.25. That's not quite right. So it's at 0.125. So 300 seconds, I'm about here, and I can continue out. So this should look like the shape of that concentration of A versus time plot that we originally qualitatively put together. But now, because we've used the integrated rate law, turned into the half-life and some actual values for the half-life and starting concentrations, we have a much more accurate picture of what this looks like. Now, just in terms of labeling and what you will see in some of the problems, this time period here is 1 half-life. And so also, from 100 seconds to 200 seconds is 1 half-life. So you will see some problems that say, how much is left after 3 half-lives or something like that. So we would go 1 half-life, 2 half-lives, 3 half-lives for this kind of problem. So we're saying this whole space is now 3 half-lives. So just so you know what the problem is asking you for, if the half-life is 100 seconds, it asks you for the concentration after 3 half-lives. It's asking for 300 seconds.